exponential growth and then the exponential decay. Okay, so on page 529, let's look at number 8. We're told that in the year 2000, the population of the Palestinians in the West Bank, Gaza Strip, and East Jerusalem was approximately 3.2 million. By 2050, it is projected to grow to 12 million. Use the exponential growth model that will be given to you. A of t equals a0, e to positive kt, of course. It's exponential growth, in which t is the number of years. T is the number of years since 2000, which means the year 2000 represents t equals 0. To find the exponential growth model function that models the data. And in part B, they're asking us in which year will the Palestinian population be 9 million. T equals what? Okay. So they're giving us basically two ordered pairs. This is one ordered pair, and you'll help me write it, and this is another ordered pair, and you'll help me write that. So since 2000 is 0 for t, I will have 0, 3.2, and since 2050 represents year 50, right, comma 12. So these are the two ordered pairs given to us. From these two ordered pairs, what will I need to determine? This doesn't need to, this is the function, or y value. That will always be there. This is the x, or the independent variable. What I don't have is this, and I don't have this. I don't have the k, the growth rate, and I don't have the initial value. So these two ordered pairs will help us determine these two unknowns. So our first step would be to just think in terms of, you know, this point, 0, 3.2, really means that when the independent variable is 0, the dependent variable is 3.2. And I can create this equation. The left-hand side is a of 0, which is 3.2. The right-hand side is a0, e to k times 0. When the independent variable is 0, the dependent variable is 3.2. So then I have 3.2 equals a0 times e to k times 0. But k times 0 is 0, and e to 0 we know is 1. We didn't have to do all this analysis, but I'm preparing it. The discussion is just preparing us for the second point. So we know now that the initial population was 3.2, which we knew basically from the get-go. So what I have right now is this. It's not done because I haven't finished. I haven't found k yet. But now this is when the second point comes into play. Like before, what does this mean? It means that whenever time is 50, the dependent variable a of 50 is 12. So I will just mimic that. Basically, I have 12 on the left-hand side. I have 3.2 times e, 50 times k. This equation will help us determine k. But what is the first step here? What do I have to do first?
Clean it up, move the 3.2 to the other side.
Careful. Excellent idea. But remember, it's multiplied. Yes, that's what I need to do, but I can't move it. There must be something else I have to do since it's multiplied. I would have moved it if I had a positive or negative. But since it's multiplied, I have to
divide it.
excellent. So then e to 50k equals whatever. Do not touch that, there is no need. So now, like before, you see a pattern in all these problems, I'm sure. We apply natural log. And the left-hand side becomes, of course, 50k, because I'm not going to write natural log e since it's 1. And this is natural log of 12 divided by 3.2. And from here, obviously, I divide both sides by 50. Please be very careful. We cannot separate. You taught me something, Ben. I should have said that all the time. We cannot separate these. This is the numerator, and we divide by 50. So the numerator is this. You cannot divide inside or anything. This is together, one number. So let's plug it in. So natural log 12 divided by 3.2, that's for the numerator. And now we divide by 50, and we get, please, on these problems for k, take at least 4 decimal digits. 0.0264. That's good enough. We finally have the model. We are happy now. Here's the model, 3.2, e to this, 0.0264t. Completely known. Done. Now the question is also asking us to find in which year the population will reach 9 million. How do I do that? So this was part A and this is part B. How do I determine Well, obviously I have to replace a of t by 9, and I proceed exactly with the same identical steps. Like before, I will divide both sides by 3.2. I will apply natural log to both sides. I will have natural log 9 over 3.2 equals 0.0264t. And of course, I'll divide by this number. Again, this is a compact number. No one can change that number. So just write the fraction line and write 0.0264 and this number at the top. So let's determine, according to the model, when the population should be 9 million. So this is natural log. I have natural log of 9 divided by 3.2. Close the parenthesis, and we divide, and I can recall the number, so I don't have to put it in. And it gives me a better approximation. I got 39.1 years. So t approximately 39.1 years. Which means roughly in the year 2039, hopefully there is no tragedy happening on this planet anymore. So the population, everyone will live in peace, and they will reach this. 9 million in 2039. So this was the exponential growth model. Let's talk about the exponential decay. And now I would like to use Ben's problem, so I'm looking at it right here. Okay. So we're told in this problem, this is problem, so it's number 1 when you get to 4.523. Question 1. I don't know if it's from a quiz or whatever it is, but that's when you get to that, so this is what we are asked. Complete the table shown to the right for the half-life. So we have to talk about first about the half-life. And then we'll choose another problem besides this one. Okay, so half-life of a substance as an example. Let's suppose I take 100 milligrams of some medication. Since I just did a problem with my other class for aspirin, I'm going to say I take aspirin. And after I take the aspirin, 12 hours later, the aspirin in my bloodstream from 100 milligrams, it drops to half. Because we are told, and they experimented that, they calculated that, and they said aspirin has a half-life of 12 hours. Every 12 hours, what I have in my system, assuming I don't take more, I only took 100 milligrams, let's say I woke up and I took 100 milligrams of aspirin. 12 hours later in my bloodstream I have 50. 12 more hours later, which is 24 hours later, tomorrow morning, I will have only 25. Another 12 hours later, I will have 12.5, and so on and so forth. Which means, which is the meaning of the half-life. Every 12 hours, what I have, it's divided by half, by 2, all the time, till eventually it will approach 0. But it will take a while. So in this problem, we are told that the half-life we are told in this problem that the half-life, which is normally denoted by age, so for the aspirin, the half-life will be 12 hours. I know it's age and age, so it's a little bit confusing, so I'm going to write hours. So the half-life is 12 hours for aspirin. For this substance in the problem, in problem 1.4.5.23, is given to us as 3.898 years. So in this particular case, as an example, let's say we have A0, which is the initial value or amount of substance. I have no idea what it is and I don't care what it is. We have A0 amount or quantity of the substance. And I know that this amount, after 3,898 years, will become A0 over 2. Today, this point is 0, comma A0. In 3,898 years, it will be A0 over 2. So, and I can continue. If I multiply this by 2, then I divide this by 4, and so on and so forth. I can create as many points as I want. Now I know that the radioactive decay model is this. Identical with what we covered a few minutes ago, what we looked at a few minutes ago. Identical, it's just that it has minus in front. Because it's a decay rate, it's not a growth rate. When the base is greater than 1, it's a growth rate. When the base is less than 1, it's a decay rate. That's the only difference. Okay, so if I plug in this point, because that will not give me anything, right? It's the same thing. So if I plug in this point like we did a few minutes ago, when t is 3.898, a of t is this. So A0 over 2 equals A0 e to negative k times that, times 3.898. Like before, you see the pattern. What did we do next? Of course we divided by this. So we can apply log. Same thing here. So when I divide by A0, A0 goes away. The left-hand side is 0.5. The right-hand side is e to negative 3.898k. Exactly like we've just looked at. Natural log of 0.5 equals negative 3.898k. I should write times natural log e, but that's 1. So then k equals natural log 0.5 divided by -3.898. Yes, this is a formula. I just don't like giving more formulas to remember. So any radioactive decay rate is natural log of 0.5 or 1/2, always divided by what you get as the half-life. If you want to memorize this formula, you can go ahead and do it, and you don't need any other explanation, but this is way more valuable what we're doing here with a point. It's up to you. So then we divide. I don't know, let's say it says round to 6 decimal places. I completely agree. K has to be as accurate as possible. So we have natural log of 0.5, and we divide by, careful, in parentheses, -3.898, close the parenthesis, and press enter. So it's very tiny, because it needs 4,000 years to get half, right? So in this case, K approximately, look at 10 to -4. 1, 2, 3. 1, 7, 1, 2, 3, 4, 5. The next one is 7, but the next one is 8, so I have to write 8. 2, 4, 6. 10 to -4. Right? So 1, 2, 3, 4, 7, 8. So this is the radioactive decay rate for this substance. If you want, you can write it, but it's not, don't write it in percentages, but I'm just giving it to you in percentages as well. 0.0178%. Very tiny. Ben, is this okay? Anyone? Is this okay?
It is. I just thought that I had punched it into the calculator wrong when I got e to the -4, and because I put in 1.7 blah blah blah, and I was like, what the heck am I doing wrong? But I see what you did.
Yes, so it's very tiny. It has this negative e raised to the power -4, which means you have to move the decimal point 4 spots to the left. Is that okay?
Yeah, that makes sense. Thank you.
Thank you. Okay, so let's look at another radioactive decay. And I'd like to do that aspirin thing that I just mentioned. Let me see if I find it. Or, yeah, let's do the aspirin. And also, there is one other interesting one that I found with the other class. So, aspirin is number 30 on page 530. The half-life of aspirin, as I mentioned, is 12 hours. Okay, how long will it take for the aspirin to decay, time to decay to 70% of the original amount of the original? How long it would take? Now, we can determine K with the formula. I don't like to use that formula, but it's up to you. I have to write the model for the radioactive decay. And I have to determine K first. So we just discovered that K equals the natural log of 0.5 divided by H, which is 12. So we can immediately find that if you would like to use the formula, or I can determine everything step by step with a point, which will take us to the same thing. It's up to you. The only reason I said that is because the problem was really asking us to use the formula, which I don't really want to give formulas to memorize. But, so we want to go.
Work the steps,
Yes, yes, I completely agree. I completely agree. Okay. So first of all, whenever I'm given the half-life, I know that that is a point. Half-life is a point. So after 12 hours, the initial value becomes half of it. Right now, at 0, I took this amount. Time 0. At this moment, I take aspirin, this amount. Nobody cares what it is. But we know that this amount in 12 hours will become half. If I took 100, this would be 50. If I took 200, this would be 100. And this is the point I need to use here. When t is 12, the function value is a0 over 2. a0 over 2 equals a0 e to negative k times 12. Yes, of course, like before, we have to get rid of a0 because first of all, I don't even have it and it's the same. Who cares? So the left-hand side is 0.5, the right-hand side is this, and we apply natural log, and we get that. So from here, we have k equals natural log 0.5 divided by negative 12. Careful with the formula, because the formula does not take into account the fact that there is a minus here. So be careful with this. So then k, we don't have to really take 6 decimal places, but I would recommend at least 4, definitely. So natural log 0.5 and divide in parentheses by negative 12. So this is 0.05776. I'm going to use 5 in this case. So we have the model. A of t equals a0 times e to negative 0.05776 t. So we found the model, so we can answer the question. Now, the 70% of the original amount is another point, for which we do not have t. T, comma, 70% of is multiplication, so it's 0.7, 70% of a0. So we do not have the time required to pass so that we get from 100% to 70% of the original amount. 100% of a0 down to 70% of a0. We don't know the time. This is again the same kind of point. When 0.7 a0 equals a0 e to negative 0.05776 t. Of course, the same thing, I need to get rid of that number. Furthermore, I don't even have it. And there's the same, I have to simplify. 0.7 equals negative 0.05776 t. And we solve for t. Natural log 0.7, negative 0.05776. And the t is approximately, have no idea, natural log 0.7 divided by, in parentheses, negative 0.05776, close the parenthesis. So in approximately 6.2 hours. So, which makes sense, because it takes 12 hours for 100% to become 50%. It takes 6 hours for 100% to drop to 70%.